Okay, so the purpose of this recording is to demonstrate the calculation of the mean absolute deviation using the TI84. What we're going to do is I'm going to use an example that you've already got in your note from the first lesson on statistics. And essentially what we're doing is I'm going to use the list function on the calculator in order to find the numerator of the mean absolute deviation calculation. And so each of these represents an individual data point. This represents the average of the data points, and what we're interested in doing is taking the absolute value of that difference for each term in the list and adding those all together. So that's going to give us the numerator. And then when we get that value and we divide by the number of numbers, that's where we get the mean absolute deviation, or I'm going to abbreviate that and refer to it as the MAD. Okay, so the example that we're going to use is the very first example over here, which shows calorie counts for 18 different brands of meat hot dogs. And so the first thing is we need to do is enter that into our list. So what I've done is I've gone ahead and I've done that already. So we would go stat, select the edit, and in list 1 I've already gone ahead and I've typed those values in. Two steps. What we need to do first of all is figure out what the average is of the calorie counts. And so we're going to start off by finding that average. So to do that, we'll quit out of the list menu. What I want to do is push stat, scroll across to calc, and I want one variable statistics, number 1, and I need one variable statistics for list 1. So I'm going to use second function and press the number 1. That'll paste L1 for list 1 in there, hit enter, and what I'm interested in is that number over there, the X bar number 169.38 recurring, and so that is the mean. And so that is the average calorie count for our hot dogs, assuming, of course, that I have entered all of the data values correctly. Okay, and so we have an average of 169.38 recurring. Okay, so I'm going to go back to the calculator. What we need now is to go back into the lists, and I now need to enter a formula for list 2 so that it can generate the list 2 values. So if you scroll up with your cursor key onto the L2, so the highlight's on L2, and hit enter, it pastes your cursor into the bottom here, and this allows you to enter a formula. The formula that I need is the absolute value of the list 1 values minus the average, which I've calculated over here on the right hand side. So to get the absolute value sign, I'm going to go into the math menu. I'm going to scroll across 1 to NUM, and the very first one is ABS, which stands for absolute value. So I'm going to hit enter. That pastes that into the formula line. I need the absolute value of list 1, so once again second function number 1, absolute value of list 1 minus, and this time I'm going to type in the numerical value 169 point, and I'm going to use 39, just use a rounded value, close the parentheses, and what that's going to do is take 169 away from each of the values in the list and take the absolute value of those to eliminate any negatives. So here we can see our list of values, and effectively what I'm interested in now is the average of that list, and that will give me the mean absolute deviation. So I'm going to quit out of the list menu, and I'm going to go second function enter. That recalls the previous entry, and I'll just replace list 1 with list 2, and so I'm going to do one variable statistics for list 2, and that yields the average of list 2, and of course the average of list 2 was the mean absolute deviation, which is 18.81. Okay, and that's it for the calculation of the mean absolute deviation. What we'll do now as well is I'm going to demonstrate briefly the use of the calculator in graphing of quadratic models or functions. And so what we have here is a quadratic function which is modeling the flight of a football, which is flying in a parabolic flight path, and so the height of the football for different times is given by the function minus 16t squared plus 45t plus 2.5. And what we're going to do is use the calculator to answer most of the questions in this example. So I'll go back to the calculator. What I need to do now is go into the y equals menu. We are now graphing a function. And so first of all, what I'm going to do is enter the equation. So I'm going to enter that as minus 16. And note we can't use t, even though you do have t. If you look above the number 4 in green and the alpha menu, you do have t, but your calculator does not treat that as a variable, and so you cannot use that. What you need to use is the x value. And so minus 16x squared plus 45x plus 2.5. And what we'll do is we'll go straight to the graph, and depending on what your graph window is, you may see some part or none of the graph at all. And so what we can do to begin with is go to the zoom, and we can start off, one of the effective methods is to start off and select zoom fit. Now the zoom fit is intended to give you a window which fits the graph that you've entered. It can be a little bit unpredictable, doesn't always work to give you the window you need, so it's not a bad starting point. We'll select zoom fit, and what you can see here is that we can see a little more of the parabola, but if I go into the window settings, you'll see that it's set minus 90 as the x minimum and 914 as the maximum, and we're definitely not interested in negative time. And so what I'm going to do is include some negatives. We want to be able to see the axes, but I'm going to just start that at about minus 2. This is a little bit of guesswork, so you may have to come back into the window 3 or 4 times if necessary in order to get the window right. And so I'm going to go in for the x maximum. Again, I'm not 100% sure, so I'm going to start it off at about 15. The scale isn't too important. The default setting is 1. If you left it at 1, that would be fine. Y minimum, as you can see here, it's starting with an enormous, an enormously small Y minimum, and so we are only interested in positive heights because this represents, the model represents the height of a ball, and so we're going to enter that. Once again, I'll enter that as minus 5 to go just a little bit below the axes, and then the maximum I definitely need a positive. I'm going to estimate that's going to be around about 45. Now if I go back to my graph, now we can see I have a much more appropriate window for finding what I need to find. What I have got obviously is too much x-axis here, so if I go back into the window, what I might do is modify that to, let's try 5, and we'll see how that goes. So now we have a much better fit for the graph. Okay, so we can now go ahead and answer some of the questions. So the first one's asked us to sketch and label, so of course I would transfer what you see on the calculator to the axes below. I'm not going to do that now. The main purpose of this is just to show the use of the calculator. One of the questions that is asked for, however, is the vertex and also the y-intercept. So we'll start with the y-intercept. You can use the graph function, go to second function, trace, and that'll allow us to access the calculate menu. And so I'm going to start off with number 1, calculate a value. This is going to give you a y value when you enter the corresponding x. I want x equals 0 because that will give the y-intercept. And in this case you can see 2.5. Of course we could very easily have read that directly off the function because it is simply the value when x is 0, which would, or in this case t is 0, which would eliminate the first 2 terms and leave us with 2.5. We also need to find the vertex, which is the turning point. So if we come back to the graph, obviously that is going to be a maximum in the context of this problem. So once again, back into the calculate menu, and I'm going to select number 4 for maximum. And what the calculator needs at this point, theoretically a graph could have multiple maximums, or we might be interested not in a turning point but just a maximum within a given domain. So basically what you need to do is get a point to the left of the one you're after. That's going to be our left bound. You can scroll there or type a value in, either way. And then I need a point to the right, so you'll notice I'm going to use the cursors, go over the top, and back down the other side a little ways, not too far. Hit enter again. The calculator prompts you for a guess. This isn't actually necessary. You could just go ahead and hit enter, and now we have our maximum 1.40625. So I'm just going to round that off. We have our maximum at 1.41 and 34.1, and that would represent the time, because that would be our x value. After 1.41 seconds, the ball reaches a height of 34.1 feet in this case, as you can see from the problem. Okay, so what does the y value represent? Of course, the calculator doesn't answer that for us, but that would be the starting height of the ball. So find the maximum height that the ball reaches and at what time. So that actually has been answered by finding the vertex. That was the maximum height and the time at which that height occurred, which was 1.41 seconds after being punted or kicked. And now we have D as the ball descends, so the ball is on its way back down. So if you look at your parabola, of course that's going to be on the portion to the right of the vertex where the height is decreasing. That indicates descending. And we have the ball being caught at a height of 5.5. So you'll notice that what's given is height, and height is a y value. And so what we're going to do to solve this problem is go into the y equals, and we're going to enter a separate function, and that function is going to be y2 equal to 5.5. And what that's going to produce for us on the graph is a horizontal line, which represents the time or times, in this case, where the ball is at a height of 5.5. You'll see there's one intersection point very close to the y-axis. That, of course, is when the ball is initially kicked, and so the one we want is the second point of intersection. So once again, into the calculate menu. This time we want number 5, the intersection. First curve and second curve. The calculator prompts you for this because you could have many curves. In this case, we only have 2 curves graphed, so I'll just go ahead and hit enter. When it prompts me for second curve, I'll hit enter. And then again, the guess. In this case, it's somewhat important. We want to go closer to the point of intersection that we're interested in, and that is as the ball descends. So we don't want to calculate the intersection point close to the y-axis. We want the one further to the right. So I move the cursor closer, hit enter, and that yields my point of intersection. You'll see the x value is 2.74, which means 2.74 seconds after being kicked. The y value is 5.5. In other words, the ball is at a height of 5.5, and that's where it was caught. Okay, last one. If the ball were not caught, how long would it have taken to hit the ground? So in this case, really what we're after is the 0 of the function when the y value equals 0. So this is different. In the calculate menu, what we're interested in is a 0 of the function, because we have to, y is 0, not x is 0, and so what we're going to do is select number 2, and once again we'll get prompted for a left bound and a right bound. In this case, I pick a point to the left of where the graph cuts the x-axis, so I'm going to hit enter over there. I'll scroll past, and you'll notice I'm now in the negative y's, so that would be a good right bound, and no need to guess. And there we have 2.87. So x would equal, or rather in this case, time would equal 2.87 rounded to 2 decimal places. And this y equals minus 1 e minus 11. That's minus 1 times 10 to the power of minus 11, which is effectively 0.10 zeros and then a 1. And so that's not perfectly accurate because of the process the calculator uses, but you can effectively interpret that to be 0. Okay, and that concludes the recording.